Alright guys, so in this video we're going to be going over problem set 1 for Organic Chemistry 2, Fall 2025. So let's get started with question number 1. So this question is asking about hybridization, and it's then asking us to determine the total number of p orbitals present in the molecule. So let's get started here. General rule of thumb, the hybridizations we want to consider are going to be sp, sp2, and sp3. So if we think about what an atom's hybrid molecules orbitals look like, for example, we have, a carbon right here, and it's going to have some hybrid orbitals coming like this. This back one is going into the plane. So in this case, if this was all bonded to something, for example, these were all hydrogens, this is going to be sp3. These are all going to be sp3 hybrid orbitals, and in this case, there are no free p orbitals because every one of them is hybridized. So general rule of thumb, we're going to put here sp3, 0 p orbitals. Okay, so if we know that sp3 is the max number of, hybridization we have, if we look at sp2, there's going to be one free p orbital. 1p orbital, and by that logic, something that is sp is going to have 2p orbitals. And this is going to be how you're going to solve this type of problem. So now let's look here at this molecule. There's a lot of hydrogens that are unlabeled, so if that helps you guys out, labeling the hydrogens is a pretty good way of ensuring that you have all of your hybridization orbitals accounted for. So whenever we see double bond, we know there's going to be hydrogen coming up like this and like this. I skipped the carbocation, we're going to cover that later. And the carbon next to it, this one here, that doesn't have any hydrogens attached to it. 2 hydrogens attached here, 2 hydrogens attached here. And for this oxygen, we have to keep in mind, because there are no charges around it, there has to be 2 lone pairs here, and same principle with nitrogen. Since there are no charges around it, we know there's 1 lone pair here. Now let's look at the carbocation. In this case, something like a terminal carbon is going to have 3 hydrogens attached to it, but because there is a positive charge there, we know that it's missing one of those. So it's going to have 2 hydrogens coming off like that. So now we have all of our hydrogens labeled. We can go ahead and start assigning hybridizations, orbitals to each of the indicated atoms. So let's start with the carbocation. It's pointing to this carbon right here, and it's attached to 1, 2, 3 separate things. So this is going to be sp2 hybridized. The oxygen here is going to be attached to lone pair here, and this double bonded here. So in this case, this is also going to be sp2. Now let's look at the next carbon over. This is attached to 1, 2, 3, 4 unique structures. So in this case, this is going to be sp3. And in the final instance, we have this carbon here, which is just going to be attached to 1, 2. So in this case, it's going to be sp hybridized. All right, and now that we know the different hybridizations of these, and we have this little table here, or this little chart thing that we made earlier, we know the total number of p orbitals in the entire molecule. A lot of you guys just put, the associated p orbitals for the labeled atoms, but in this case, we need to read the question carefully. It says in the molecule. So we look here. I'm going to do this in light blue. This sp2 hybridized carbon right here is going to have 1 free p orbital. The one right next to it is going to have 1 free p orbital because it's sp2 hybridized. Same thing goes with here. Same thing goes with here. And the one next to this one, this carbon right here, this is going to have 0 p orbitals because it is sp3 hybridized. Same thing with this sp3 one over here. The sp hybridized carbon is going to have 2 free p orbitals. And then the last one, this nitrogen here, is going to have 2 free p orbitals. Alright, so I totally missed this carbon right here, that is the carbonyl carbon. Since that is sp2 hybridized, we know it's going to have 1 free p orbital. So if we add up all of the p orbitals, we're going to have a total of 9. So now let's move on to nomenclature. So for nomenclature, the first thing we want to think about is finding the longest carbon parent chain. So in this case, it seems pretty obvious. We have 1, 2, 3, 4, 5, 6, 7, 8. That is going to be our longest parent chain. And our next conundrum is seeing whether we want to number it left to right, starting with carbon 1 here, or right to left, starting with carbon 1 number here. And in this case, we want the highest priority parent, and that's going to be coming off of carbon number 2, so we know this alcohol is going to take priority, and we're going to name, or I guess number, from left to right. So we got 1, 2, 3, 4, 5, 6, 7, 8. So we know it's going to be an octan all of some sort because we have the alcohol. So now let's take a look at the branches. What I like to do is I like to name all of my side chains. So all, we're going to put that up there. We're going to put like butanol over here just so we don't lose anything. Next most obvious thing is the carbon coming off of carbon number 7. This is going to be methyl. And if you guys have any questions, it doesn't really matter if your 8th carbon is the one going up here or down here. It doesn't really matter. They can all freely rotate. They all are sigma bonded to one another. So now the most trickiest, I guess, side chain that I saw a lot of students struggle with is this branched branch. So we want to be as specific as possible following the rules and not account for one of the methyl groups. So we know this is coming off of carbon number 6, and we have a methyl here and a methyl here. So we know we're going to have a dimethyl, and it's coming off the end, so it's going to be an amino of some sort. And we haven't yet designated where the methyls are, and they're coming off of the nitrogens. And since there's 2 of them, it's going to be N, N for something that looks like this. Okay, so now we have all of this, our little side chains labeled. We can go ahead and name the primary chain. So we have 6 N dimethyl amino 7 methyl octan -2 all. Alright, now let's look at the second molecule. So we have the longest number parent chain, 1, 2, 3, 4, 5, 6, only counting carbons. We're not including any other atoms right here. This is going to be 6 carbons long. And then again, we're stuck. Do we start naming left to right, or do we start naming right to left? So now we basically need to consider the fact that stereochemistry takes into account here, and in this case, the fluorine is going to take priority. So we're going to start naming 1, 2, 3, 4, 5, and 6. All right. So we can go ahead and name this. We know this is a 3-fluoro of some sort. Make sure to spell fluoro correctly. And this group coming off of here, this is a 4-methoxy of some sort. Alright, but we're not yet quite done. We also need to account for the double bond that spans between carbon 3 and 4. So we always want to start with the numbering of the lower of the carbons. So between carbon 3 and 4, we know it's going to be a 3-ene of some sort. Alright, and with double bonds, we must take into the fact that it can either be E or Z isomers of one another. So a little trick I like to say is we're going to look at the masses of the compounds that the double bond is attached to. And in this case, the ones that are the heaviest are going to be fluorine and oxygen. So you can go ahead and highlight in this light blue. It's going to look like this. I'm going to draw off to the side. If your double bond spans like this, and this is your double bond, this is going to be E, And if it spans in the same way, this is going to be Z. And the way I like to remember it is that Z is when the two heaviest atoms go the same side, like same side, while E, the two heaviest atoms go the opposite, or I guess opposite side. Just a little mnemonic that I use to, know which one is E and Z designation. So now we can go ahead and name this molecule. So we're going to start off with E, 3-fluoro, 4-methyl, and then we know it's 6 carbons long, hex -3-ene. Alright, so we're going to be reviewing arrow pushing now, everyone's favorite. So we have this hydrocarbon reacting with HCl, and we're going to have to draw the mechanism. So we know in this case, nucleophiles and electrophiles, in this case the double bond is our nucleophile of interest. So in this case, this double bond is going to go ahead and attack this hydrogen here. And what goes around comes around. If this is going to attack the hydrogen, this double bond needs to, or the single bond, sorry, must go and jump onto the chlorine, giving this chlorine 1, 2, 3, 4, 5, 6, 7, 8 electrons and making it negatively charged. So now we have here, we need to account for the carbocation as well. So if the hydrogen goes ahead and jumps there, the carbocation is going to form here. All right. But it is really important to know, and we're going over in class right now, that hydride shifts must be accounted for. So this carbocation sits on this carbon, which is secondary. And if we look at the adjacent carbons, we see to our left right here, we have a tertiary carbon. And in this case, that is going to be the more stable structure. So we know there's going to be a shift that occurs. So the positive charge is going to end up here. And we have the chlorine that is negatively charged here. And in this case, this is going to attack the electropositive carbon here for a final structure that looks like this. And let's say even if we didn't know there was a shift that occurred, if we just looked at our product, we would, call into question and be like, that's a little weird. Something must have happened there. So in this case, this is this problem. And the last problem, we're going to be asked to draw some resonance structures. So the most important thing with resonance structures is the fact that only electrons move and carbons or other atoms don't move. Another important thing is that we want the charges to remain the same throughout. So for example, I saw some of you guys had negative charges on one of your resonance structures for a total of -1, while on your other structures you guys had, a minus and a plus for a net charge of 0, which doesn't really make sense because you can't really create or destroy charges like that. So in this cases, for this first molecule, we have 2 resonance structures that we're being asked to draw. So in this case, the most easiest thing we can do here is have this pair of electrons here swing up here, and now there's going to be a deficiency on this carbon, so this is going to swing down here for a resonance structure that looks like this. And every time you draw a resonance structure, ask yourself, did I only move the electrons, and is the charge still the same? And in this case, the answer is yes to both of those questions, so we know we're good. So the next resonance, we're going to be pushing the most obvious thing whenever we see carbonyl structures. Typically, we know that the double bond can swing up to the oxygen because it is a very electronegative atom, and that is going to be favorable. And if that goes up, there's going to be a deficiency right here on this carbon, so these electrons are going to swing down. Sorry, it's all in purple. It might be kind of hard to see. So we have a final structure that looks like this. Alright, negative charge lands on the oxygen. Double bond, double bond. So now it's also going to ask us to circle the resonance contributor that contributes the most to the hybrid. Remember that all of the resonance structures assume a hybrid formation, so the actual molecule doesn't actually look like any of these, but a hybrid of both that looks a little something like this. There's going to be like dotted lines that indicate that there's resonance all around here. So all of these are contributors, but the one that contributes the most is the one on the very right. And that is the case because the most electronegative atom here is oxygen, and that has the negative charge, and that is going to be very stable. Now, last question here, another resonance thing. We have a carbocation here and a double bond next to it, and typically we know that there's a deficiency, a free orbital here that the electrons can jump to. So this is going to door hinge over and swing over there. And we're going to have something that looks like this. A double bond is going to land right here, and the positive charge is going to end up here. Same scenario, which one is going to contribute most to the hybrid? And in this case, the rightmost structure is, because the carbocation is tertiary, while the one in the first structure is only secondary. And remember that these are hybrids, so none of these structures are actually what it looks like. It's a mixture of both that looks a little something like this. Alright, hope this video helps.